Good morning. I'm Devasena. In this lecture, we are going to discuss about half wave rectifier and application of diode. Before going to discuss about the operation of the rectifier, let us discuss about the function of the diode. A diode is a two-terminal semiconductor that acts as a one-way gate to electron flow. That is, the diode allows current to pass in only one direction. A p-n junction diode is formed by joining together n-type and p-type silicon. The p-type is called anode and n-type is called cathode. When the anode and cathode of a p-n junction diode are connected to external voltage such that the potential at anode is higher than the potential at cathode, then the diode is said to be forward biased. In a forward biased diode, current is allowed to flow through the device. Let us see the pictorial representation of a diode. Now we see the symbol of the diode. Let us see the applications of the diode. In a forward biased diode, current is allowed to flow through the device. When potential at anode is smaller than the potential at the cathode, the diode is said to be reverse biased. In a reverse biased diode, current is blocked. So far we have seen the function of the diode. Let us see how the diode is used as a rectifier. A rectifier is a device which converts AC voltage to pulsating DC voltage with the help of one or more p-n junction diodes. The p-n junction diode subjected to an AC voltage acts as a rectifier, converting alternating voltage to a pulsating DC voltage. Let us see the types of rectifiers. There are various types of rectifiers. They are half-wave rectifier, full-wave rectifier, bridge rectifier. Let us see the operation of the half-wave rectifier. Half-wave rectifier consists of a resistive load, a rectifying element, that is single p-n junction diode, and the source of AC voltage. These components are connected in series. The figure shows the half-wave rectifier and its corresponding waveform. To obtain the desired DC voltage across the load, the AC input voltage is applied to the rectifier circuit with the help of suitable step-down transformer with necessary turns ratio. The input voltage to the half-wave rectifier is a sinusoidal AC voltage having a frequency with the supply frequency 50 Hz is given by E suffix sm is equal to capital E suffix m sin omega t, where omega is equal to 2 pi f and the f indicates the supply frequency. The transformer decides the peak value of the secondary voltage E suffix sm. Let us see the operation of the half-wave rectifier. A sinusoidal input voltage is applied to a half-wave rectifier. Sinusoidal input voltage comprises of a positive half cycle as well as a negative half cycle. During positive half cycle of the input AC voltage, the diode is forward biased and the current flows in the circuit in the clockwise direction. During negative half cycle, the diode is reverse biased. Due to this, no current flows in the circuit. This is the circuit current, which is also the load current, is in the form of half sinusoidal pulses. The load voltage, being the product of load current and load resistance, will also be in the form of sinusoidal pulses. The peak value of the load current is given by I suffix m is equal to E suffix m divided by Rf plus Rl plus Rs. Let us represent the AC input as capital V suffix I is equal to capital V suffix m sin omega t, where V suffix m represents the maximum value of the AC signal and omega its frequency. Since the output voltage capital V suffix O is obtained from only one half cycle, V0 is given by V0 is equal to Vm sin omega t for 0 less than omega t less than pi. It is equal to 0 for pi less than omega t less than 2 pi. Hence, I is equal to Vm sin omega t, that is equal to Im sin omega t. Therefore, I is equal to Im sin omega t for 0 less than omega t less than pi, and its value is equal to 0 for pi less than omega t less than 2 pi. The average or DC value, that is I average is equal to IDC, that is equal to area under the curve over full cycle by base. Let us see average or DC value of the current. IDC is equal to 1 by 2 pi integral of 0 to 2 pi Im d omega t. Substituting the value of Im, we get 1 by 2 pi integral of 0 to 2 pi Im sin omega t d omega t. The integrals are split into 1 by 2 pi 0 to integral of 0 to pi Im sin omega t d omega t plus integral of pi to 2 pi Im sin omega t d omega t. That is 1 by 2 pi integral of 0 to pi Im sin omega t plus 0, because from pi to 2 pi there is no output, being a half-wave rectifier. That is 1 by 2 pi integral of 0 to pi Im sin omega t d omega t. After applying the integrals, we know that integral of sin omega t is minus cos omega t. We get Im by 2 pi minus cos omega t. The lower limit is 0 and the upper limit is pi. After applying the limits, IDC is equal to Im by 2 pi cos pi minus cos 0. IDC is equal to Im by 2 pi minus 1 because the value of cos pi is minus 1 and cos 0 is 1. Therefore, we get IDC is equal to Im by pi. Similarly, the value of VDC is equal to Vm by pi. Let us see the RMS value of the load current IRMS. IRMS is equal to square root of area under the square rectified wave over a cycle by period or base. That is, IRMS is equal to square root of 1 by 2 pi integral of 0 to 2 pi I square d omega t. That is, square root of 1 by 2 pi 0 to 2 pi Im sin omega t the whole square d omega t, because the value of I is equal to Im sin omega t. Square root of 1 by 2 pi 0 integral of 0 to pi Im sine omega t the whole square d omega t plus integral of pi to 2 pi im sine omega t the whole square d omega t. Its value is equal to square root of im square by 2 pi integral of 0 to pi sine omega t the whole square d omega t. That is im square by 2 pi integral of 0 to pi 1 minus cos 2 omega t by 2 the whole square d omega t, because the value of sine square omega t is equal to 1 minus cos 2 omega t by 2. After applying the integrals and applying lower limit and upper limit, we get square root of im square by 2 pi omega t minus sine 2 omega t by 2. The lower limit is 0, the upper limit is pi. That is, finally we get Irms is equal to im by 2 and Vrms is equal to im RL by 2. Let us obtain DC power output P suffix DC. DC power output is equal to EDC into IDC. Substituting the value of IEDC, we get IDC square RL. Therefore, the value of the P suffix DC is equal to im by pi the whole square RL, because the value of IDC is equal to im by pi we already obtained. So we get PDC is equal to ESM square by pi square into RF plus RL plus RS into RL, because the value of im here substituted as ESM by RF plus RL plus RS. Let us obtain AC power input PAC. The AC power input taken from the secondary of the transformer is the power supplied to three resistance, namely load resistance RL, the diode resistance RF and winding resistance RS. The AC power is equal to PAC, that is Irms square into RF plus RL plus RS. But we know the value of the Irms. Irms is equal to im by 2. This is for half wave rectifier. Therefore, P suffix AC is equal to im square by 4 into RF plus RL plus RS. Let us start discussing about the efficiency of the rectifier. It is represented by a symbol eta. Rectifier efficiency is defined as the ratio of the DC output power P suffix DC to the AC input power P suffix AC. It is represented by a symbol eta. That is, eta is equal to P suffix DC divided by P suffix AC, where P suffix DC is equal to IDC square into R and P suffix AC is equal to Irms square into RS plus RF plus R, where the value of RF is equal to forward resistance of the diode and the value of RS is equal to secondary resistance of the transformer. Substituting Irms is equal to im by 2 and IDC is equal to im by pi for half wave rectifier, we get eta is equal to im by pi the whole square into R divided by im by 2 the whole square into RS plus RF plus RR. That is, eta is equal to 4 by pi square into R divided by RS plus RF plus R. If we consider the value of RS plus RF is very less when compared to R, then we can neglect the value of RS plus RF. Therefore, the eta is equal to 0.406 into R by R. That is, eta is equal to 0.406. Or in terms of the percentage, the efficiency eta is equal to 40.6%. The maximum efficiency of a half-wave rectifier is 40.6%. Let us obtain the equation for ripple factor nu. The unwanted AC components present in the DC output are called as ripple. Ripples can be removed by using filter circuits. Ripple factor is defined as the ratio of the effective value of RMS value of AC component of voltage or current to the average value of voltage or current. That is, IRMS is equal to square root of IDC square plus I1 square plus I2 square, or IRMS is equal to square root of IDC square plus IAC square. Where I1, I2 are RMS value of ripple components such as fundamental, second harmonic, etc. respectively. The ripple factor gamma is equal to IR RMS by IDC. This is equal to IAC by IDC. The value of IRMS is equal to square root of IDC square plus IR RMS square. Is equal to square root of IRMS square minus IDC square by IDC. That is square root of IRMS by IDC the whole square minus 1. For the half-wave rectifier, IRMS is equal to Im by 2 and IDC is equal to Im by pi. Therefore, ripple factor is equal to square root of Im by 2 by Im by pi the whole square minus 1. That is, ripple factor is equal to square root of pi by 2 the whole square minus 1. After simplifying the above expression, we obtained ripple factor is equal to 1.21. From this expression, it is clear that the amount of AC present in the output is 121% of the DC voltage. So, the half-wave rectifier is not practically useful in converting AC to DC.